All right. Thank you, Max, for the introduction. And thank you for all coming. And today we're going to talk about the dissipation obstacle in the port-Hamiltonian framework. And I'm going to propose a contact port-Hamiltonian framework that overcomes this obstacle. So let's start with this port-Hamiltonian framework. What is it and why is it important to us? Well, the port-Hamiltonian framework is a method with which we can energy-based model and control systems. And for us, this is very important because we have an analogy between energy and economic surplus that allows us to use this framework to build and model and control economic systems. So at the top here, we have a very general representation of a port-Hamiltonian system. We have a couple of elements. For example, the blue one is the energy storing element. And for economic systems, this will correspond to surplus retainment. So let's look at an investor, for example. At the bottom right, here is a schematic, an analog between a spring mass damper system and an investor. We also have some energy here, some surplus, and that is basically two parts. So we have indirect surplus and direct surplus. The direct surplus is basically the fact that the investor is buying some stock, some bonds, for example, and because he's buying these things, he's enjoying economic surplus. He could have also he was also maybe able to buy them for a higher price, but he can buy them for a set price, which might be different from his reservation price, and that will be bringing him wealth. We also have some indirect surplus, so that will be stored in the spring. So okay, I'll continue where I left off. So this investor enjoys two kinds of surplus. Direct surplus, this is the investor buying some stock or bonds, and he has indirect surplus. Those are basically the investments he has made already, and in the future he can sell them to enjoy his economic surplus. So it's very analogous to a spring mass system. We have also other elements, so that was the blue energy storage element or surplus storing element. We also have a dissipative element, which would be wise to add if you want to model dissipative systems. Again, very relevant for us because every economic system is dissipative. So for example, if we look at the bottom left, we have a supplier, and the supplier has some inventory of stock that he's keeping. He is also trading the stock, some goods. And the fact that he is storing these goods means that these goods over time will lose value. This is depreciation, and this basically means that some of that surplus that he can enjoy in the future, well, that is actually dissipating away. We can also add some external ports with which we can apply some exogenous signal, for example, an effort. So that would be an incentive for the supplier, for example. The supplier is connected to a market, and the market might have an incentive to buy the goods the supplier is supplying. Because of this incentive, also a flow of goods will come about, and we basically have our two variables that give us the flow of money, the y and the u variables. Now, in the middle, you see a large white element with a D in it. This is the Dirac structure. And this is a mathematical structure that basically ties everything together and enables us to connect these elements. So let's focus on that first element, the blue storage element. And this element alone, on its own, can describe frictionless systems. So for example, we have an investor with some indirect surplus and some direct surplus, but it will not have to pay any fees. So this is highly theoretical. And these surpluses, these indirect surplus and these direct surplus, together they add up to the total surplus. This is notified by H. And in mechanics, this H denotes the energy. This function is called the Hamiltonian, and it gives us, for any states, the amount of energy in the system. And this function is highly useful, because if we take the gradient of this function and we multiply it by a structure matrix J, we get basically the evolution of our states, the evolution of our systems. Then on the right-hand side again, we can see that if we choose these variables Q and P, these are canonical variables, and they correspond to the position the investor takes and the price of the investments. Then our J matrix has this really simple form, this 1, 0, minus 1, 0 form, and we can always choose variables such that we have this easy form. Okay, so now we can describe frictionless systems, but we can also add some exogenous ports, so some exogenous surplus allocating ports. And this basically allows us to see, okay, what if the market would have an incentive? What would happen to the supplier, for example? And in our formulation, this external ports corresponds to the green parts, and this would be the input matrix. Due to the structure, the direct structure, we have some power conserving or surplus allocating conserving structure. And because of that, our Y necessarily has this adjoint form. Now, then finally, we also want to add some dissipation. And this is also possible in port-Hamiltonian framework, but this is where things start to become a little bit weird. Because I put this dissipation as an element, so kind of equal as storage. But it's not equal to the storage at all. What is happening here is there is not energy being saved or stored. There's just energy dissipating, which we are not accounting for. Or in the economic analog, there is surplus being dissipated throughout the economy, and we are not counting this surplus. But that is actually really weird, especially if you look at economic systems. So let's look at the supplier. The supplier has some inventory. Because he has some inventory, he will also have some depreciation. And at first glance, you would think, oh, well, surely the surplus indeed is being destroyed. The supplier cannot access that lost surplus anymore. But in economics, one man's inefficiencies are another man's gain. So this surplus is not lost at all. Maybe a consumer is now able to buy this inventory for a lower price than he initially would have been able to buy it for. So that surplus is not destroyed, it's dissipated throughout the economy. And what the port-Hamiltonian framework does is it accounts for this dissipation by correcting the state equations. So we have this J matrix, which we saw was based on the Hamiltonian mechanics, these energy-based mechanics, and we add this R matrix that basically gives us like a friction force. And this is not energy-based at all. It's just a posteriori fix that they use such that they can model dissipated mechanics. Now, if you're doing modeling, this is all perfectly fine. You're not going to run into any troubles. Which makes sense. If I'm modeling, I only need to know if I'm at this position, where am I going? But suppose you want to do something like control. Then you would need much more information. You need to know, okay, if I'm at position 1, how do I go to position 2? And what will my path be? You need to know much more about the system. So we can already anticipate that this is going to cause some trouble for control. And if we look at the history of the port-Hamiltonian theory, this is exactly what we see. So in the first 10 years, from 1990 to 2000, this was the beginning of port-Hamiltonian system theory. We developed basic theories like the direct structure, those elements. They also tried to develop some control methods, specificity-based control, control by interconnection. These are energy-based controls. And in 2001, they were thought, so that is the main research groups, Ortega and von der Stoff, put out a paper called Putting Energy Back into Control. And this really put energy literally back into the control community. It was a very successful paper, but at the same time, they were experiencing some troubles. They were noticing that their energy-based control methods, BBC, CBI, were not working for systems with dissipation. So that's a huge problem because we are trying to describe dissipative systems. Afterwards, about 10 years of some more research went on into this dissipation obstacle. In 2012, at the TU Delft, there was a proposal for an active control by interconnection method. So the old control by interconnection method was passive. They thought, okay, if we can make it active, maybe we can cancel dissipation and work it out. They published it, they thought they solved it, and then 2 years later, a group, Ortega, this is the one from before, showed that actually this method is limited in exactly the same way as the old method. Now, for the past 10 years, there has been a lot of research into applying heuristic methods, so neural networks-based methods, to, on the one hand, learn these systems, but also to try to overcome this dissipation obstacle. But in my opinion, this is trying to solve a really fundamental problem with heuristic approaches. So we need something better. But before we go into how we are going to solve this problem, let's look at what is going wrong so we can really understand the problem. Let's start with that first control method, passivity-based control.
And this is an energy shaping method, but we cannot even get to the energy shaping. And I will show you why. So passivity-based control is based on the principle of passivity. A system is passive if the energy does not increase, so it only stays level or decreases. And if I have a passive system and I interconnect it with a passive controller, well, I again have a passive system, which is really useful for stability. So on the left-hand side, I have a passive system. I build my passive controller, I interconnect them. So my passive controller is just a spring and a damper. And if I choose my string strength right, then I can make this investor or this math jerk somewhat to the right, exactly the amount that I want. And at this new equilibrium, if I let the system go, there is no transfer of power. My system is really at rest. On the right-hand side, we have another really elementary system, the supplier or an RLC circuit. And for this system, we cannot do the same trick. Why? So suppose you are a supplier, you have some stock. Well, whenever you have some stock, some goods, there will always be depreciation. So if you want to track a certain inventory level, there's always going to be surplus flowing out of our system. Which means that if I interconnect a passive controller, I always need to give back some surplus. I need to inject energy in my RLC circuit. But my system is passive, so this means I will need an infinitely large battery, and that is actually exactly the same as an active element. So this doesn't work, and the mathematics also tells us this. So then we have control by interconnection, their second method. And with control by interconnection, we can do some energy shaping, but we are severely limited. We can only use non-dissipative states. So for an example, let's look at the EU economy. Let's formulate this as a port-Hamiltonian system. Let's look at our controller, the European Central Bank, for example. Let's also formulate this as a port-Hamiltonian system. Let's now interconnect them with a constant interconnection structure. And now I have a new closed loop system. So my EU economy has a certain surplus function. On the right-hand side, you can see an example of this, the H. My European Central Bank is also a system, so also has some kind of surplus function. And the closed loop system has a surplus function, which is simply the sum of these two. And what I can do, if I choose my controller right, such that it has a particular surplus function, the green surplus function, then I can shift my closed loop surplus function around. And this is really useful because we have dissipative systems. If I start at some state, I will have a certain energy and I will converge asymptotically to the bottom of these functions. These are Lyapunov functions. So the idea is, well, now if I design my controller such that my closed loop surplus function moves exactly to my tracking objective here, exactly above that objective. Then asymptotically I will approach this objective. And that's all fine and good. And you can design your controller however you want, but there is a problem. Our controller energy or surplus function is in terms of the controller states. But on the plot on the right, we are in the world of the system states. The system surplus function is in terms of the system states, and we want to express our closed loop system function, surplus function, in terms of these system states. So we need to relate the system states in the control states. And for that, we need a function. Let's call it function C. And suppose that function does not change. Well, if that is the case, then I can algebraically shift things around and express my controller states, xc, in terms of the system states. And if this function is invariant, then my closed loop system will not move about, and I can safely design my controller function. Now suppose we have some dissipative states. So for example, the Q, the inventory of the supplier. Whenever I have these goods in my inventory, I will experience this dissipation, this depreciation. Well, if that is the case, I cannot find a function that relates the controller states and these dissipative states that remains invariant, because these dissipative states will literally dissipate. They will tend to zero, so my control function will change. And in the mathematics, this also prevents us from actually designing these controllers. So this also doesn't work. So I mentioned before that Ortega and van der Schaft come together and developed a method that solves the dissipation obstacle. And in theory it does, but in practice it doesn't. So what is this IDA PBC that solves it? It's really similar to controlling interconnection, as you can see on the left. There's one difference. The interconnection structure in the middle, the I, it is not constant anymore. It's a function of all the states of the system. So suppose you are the European Central Bank. Now you have to measure everything that is going on in the system. Every price, every flow of goods, everything to be able to control. So practically already that would be very unsuitable for our purposes. The mathematics also gives us a problem because we have to solve the matching equations. And these are a set of partial differential equations that are nonlinear, homogeneous, and constrained. And at the bottom, I gave an example. This is the simplest supply rate that you can make. This is the equation that you have to solve. You cannot even solve this for the simplest system. You have to do some additional assumptions, but in this form, you cannot solve it. So for even moderately sized systems, you can imagine that this is not going to work. So we need to do something fundamentally different. And the way we are going to solve this is we are going to put internal energy back in control. And we are going to do that with contact structures. So in the red, you can see the flow that the port-Hamiltonian literature right now is taking. They start with Hamiltonian mechanics, they add a direct structure, then they go to this dissipative structure, the R matrix that corrected things, and they are able to model dissipative mechanics, but they cannot do energy shaping. What we are going to do is we're going to use Hamiltonian mechanics, also the direct structure, but we are going to build something called a contact structure. And that will take care of the dissipative laws. And this will allow us to use something called contact Hamiltonian mechanics. The name already suggests it's very similar to Hamiltonian mechanics, and that is indeed the case. No need for any correcting dissipative structure. Also, it's based on the total energy. So not only the blue energy, but also the dissipated energy that we were not accounting for. And this allows us to do energy shaping. So let's discuss our game plan. We want to add our internal energy of the damper. For example, this is a physical system. And we want to add that to the energy function we had before. And this will now give us our total energy. And this energy will be conserved instead of what we had before. The Hamiltonian function was actually not conserved. And we want to enforce dissipation, and we are going to do that with a dissipation law. So that's that alpha right there. If we set alpha to 0, then you can see that the little gain in the internal energy of the damper will be caused by the friction energy that is going on in the damper. So what we're doing on the left-hand side was what we had before. The circles are the level curves of the Hamiltonian function, and we are doing Hamiltonian mechanics, but then we have to awkwardly correct for this with our matrix, and we are going through our level sets, so there's no conserved quantity, and we are going to the right image. So now we have a new function for k. We can calculate this gradient. We can use another J matrix. It's a bit different, you will see it in a minute. And this will allow us to calculate the trajectory. And here you can see the level sets. We are perfectly on these level sets for the whole time. But the level sets are all nice and good, but they are not the point. The point is that we get rid of this R matrix, this corrective structure. We can do this in two ways. So first we can do a process called contactification. Here we add our internal energy, the internal energy of the damper, to our state space. So we augment by one dimension. And then we can find a J matrix that is state dependent in such a way that multiplying it with the gradient of the scale function gives us the suitable, the correct dynamics. We also can do a process called symplectification. Then we go up one more dimension. And if we do that, our variables change a bit, but they represent the same. We get an even nicer matrix. And this is really similar to the J matrix we had before. Okay, so this sounds all nice and good, but how do we find this magical J matrix? Well, we can use this contact geometry I spoke of before. And I will do you one better. It will also give a coordinate-free representation of the structure matrix. So let's see how we can do this. So we start with the dissipation law, that alpha I was talking about before. and we want to set this alpha to 0. What I did not mention about alpha before is that alpha is a one-form. So it's a linear function on vectors. And if you set a linear function on vectors to 0, for example in 3D, you get two-dimensional planes. So what you are seeing in this three-dimensional phase space, at every point is a little plane. And this little plane tells us the directions we can go in, such that we satisfy the first law of thermodynamics. Now, the nice thing about contact geometry is we can, at a point, look at our little plane, then we can do an operation, a really simple operation called the external derivative, and this will basically give us the J matrix in any coordinates we so choose. So this is a really nice way to build this into our phase space. And here is an animation of what is actually happening. So this is our system going through our phase space, and at every point it has a contact hyperplane. That is that plane I was talking about. And you can see whenever I have some momentum, my plane is tilting. And because it is tilting and I have to follow that plane, I am dissipating energy whenever I move it. This is for a spring mass damper system. Because I'm working with the total energy, whenever I dissipate energy, my states will converge to 0, such that the Hamiltonian will decrease. So the last part is actually pretty important, because the Hamiltonian H and that internal energy, they are opposing. And we can use this fact to do control, because the left-hand side is specified by our contact geometry, but it's kind of like the inverse of the energy function that we want to shape. So in here we see an example of how we can do that. We can define our U such that we have a certain energy shaping function. Because of the structure of our system, this energy shaping function will also mean that our closed loop system will move with it. And what you see in the right hand side is an animation of this control law being applied to a RLC circuit. And importantly, this circuit was the one before where I showed for IDA PBC the complicated formula. So you cannot solve the system with PBC or CBI, and you cannot solve it with IDA PBC, but you can solve it with this. So this shows us that we have everything we need to start doing control of dissipated systems. And that brings me to my proposal. So I want to develop a port contact Hamiltonian theory that allows us to describe these systems. I want to develop energy and passivity-based control methods such that we can control these passive systems, dissipated systems, sorry. And lastly, I want to investigate the opportunity of developing coordinate free control, because we were able to describe the J matrix and actually the dynamics of our dissipated systems by just formulating some energy dissipative law. But you can imagine we can also make the law about supplying energy, so control. So with that geometry of the phase space, we can already represent control methods. And the fact that we can use this to solve the dissipation obstacle is not the only thing. Contact geometry offers a completely new paradigm to control and identification. So the first point I already touched upon, we can do coordinate-free control, which is really nice, because after we have defined our problem and control policy, we can then choose best coordinates that simplify our simulations. That's called reduction and very much used in mathematics and physics. Also, contact manifolds are locally homeomorphic if they are of the same dimension, which basically means if I solve the dissipation obstacle for one system of dimension 3, for example, then I solve it for any system, any contact manifold of dimension 3. Now, I touched upon this process of simplification that made this really nice J matrix. We can also do that, and it is represented as a projection of a 4-dimensional space. And the trajectory that you see is really simple. And that's really important for the simplification process. You get basically the same mechanics as the Hamiltonian mechanics. You get exactly Hamiltonian mechanics, which means that the trajectories are really well behaved. And because of this, we can use symplectic solvers. These are highly efficient solvers that we can use for prediction, and these are used by astrophysicists to predict the motion of planets for millions of years without almost any error. As well, that really nice structured J matrix with the ones and the zeros, that is actually a form of the matrix in which we can always bring the system. So if we have that form, we only have the H function that defines how the system behaves. So to identify a system, we now only need to identify one function. And we have a lot of methods, for example, neural network-based methods, that are really good in finding these functions. I hope I have made you enthusiastic about using context geometry to solve the dissipation obstacle, as enthusiastic as I am. I want to thank you all for listening, and if you have any questions, I'll be eager to answer them.
Yeah.
Just out of interest, have you already contacted Ortega? Because you're probably very keen to hear about that.
Not yet,
No.
Ortega. I have had a meeting with Martin Javarian, who does nonlinear control,
Yeah.
and she told me that if I wanted, she could get us in contact with Arjen Kiesel, because she has worked with Arjen
It
Kiesel.
was the Delft guy.
No, he worked at Groningen. Yeah, they did
Okay.
a lot of work in Groningen, Mexico, a bit unusual, but this is where this stuff all comes from.
There's a guy in France too, die Maske is in France.
Maske, yeah,
Is in
yeah.
Strasbourg.
Yeah. So that's something that's really interesting, which we could look at, and that's maybe something for in the future if we develop this further.
Further questions?
At some point you mentioned that you will track the U as well now, the U system.
Yeah.
But don't you still need all the states, all the commodities you have to track the U?
Yeah.
So
Yeah. Oh, so you mean you have the same complexity basically as the IDA PVC.
Yeah, because there you also need to
Yeah.
track all these states and.
Yeah, definitely. So this is a proof of concept to show that we are in a very good shape to be tackling this problem. I have not finished my thesis, otherwise I would be giving my answer in colloquium. But this is just to show you that we have the information, the tools available to tackle this problem. And already we're doing better than IDA PPC, because IDA PPC, one, you had to track everything that's going on. Second, you can't even do it. They can't even solve this RLC circuit problem. And for the full state tracking problem, there are, of course, in the end, ways to estimate their states. But in the ideal scenario, of course, we'll be using the strict port-Hamiltonian approach.
But they could also estimate their state, right?
Yeah, but still, if they estimate their states, their problem is twofold. So they have worked on their method for a long time. This is a proof of concept. Their method does not work. This does work. And of course, they can use state estimation. But it would be very interesting to look at ways of avoiding that. And because we have this structure that basically allows us to do Hamiltonian mechanics, and when you're doing Hamiltonian mechanics with port-Hamiltonian, you do not need to estimate all the states. So this leads us to believe that there might be possibilities to achieve this.
Do you maybe already have like an economic system in mind for your proof of concept, or will it purely be theoretical?
Ooh, that's a good question. I have not thought about applying the end result to an economic system. For now, I'm really interested in the theoretical problems, and if we get to the point there that we can solve it, then because of the universality of the port-Hamiltonian framework, we can use it for any system. So if you would look at the European market, for example, and the European Central Bank, then there's no reason to believe that we couldn't use this method. We just have to bring it in a port contact Hamiltonian format.
You had an example of an electric system, a mass damage system. Is there a reason you made them different, or is it just to show that you can use both? And this, for example, method will work with both systems.
Yeah, so they are different, and they are different in the following way. So for one system, the based control works. CDI also work. But this system is actually special. We get kind of lucky. And this is what I mean. So on the right hand side, whenever we want to track some inventory, we are also going to have some supply inductance. And these are kind of linked in a way. So if I want to track anything, I'm going to have dissipation. Also at my equilibrium point, I want to go to. For this system, it just so happens to be that there is no dissipation when I'm going to this equilibrium point. This is a nice thing about the mechanical system, robotic applications. And that's the reason why port-Hamiltonian is used quite often in robotic applications, because often they get lucky. For us, this will not be the case. We will always have these kind of things. For example, this is the simplest supplier you could possibly make. Try to make a economic systems without a supplier. Does this answer your question? Or?
Kind of, because from my point of view, if you change the left-hand side, there is dissipation in the damper, right? You're not tracking it in this case. And
Yeah.
you're tracking it in the right-hand side. Is that the difference then? Because you mentioned that there's no dissipation in the left-hand model, but the damper will have dissipation.
Okay, yeah. They get away with not tracking it. Why? Because whenever they're at another equilibrium, there's no dissipation at that equilibrium. So it's kind of like their model is a bit off, but they have integral gain. So they will convert. Yeah, exactly.
I have a question. So you're saying you're putting internal energy back, and I understand that. But could you, with this, you add a variable,
Yeah.
right? Which they don't do, which is the internal energy.
Exactly.
And the internal energy can also be represented as a sort of a C element, because you can use entropy as the storage,
Yeah.
and then temperature as the force, the generalized force. So this thing, exploiting that U variable further, maybe you can make a statement that you're putting entropy back into control.
Yeah.
So that not only are you controlling for the position and the price, right?
Yeah.
But also for the heat, how hot this thing is going to get.
Yeah.
Okay. Which is not typically what we do. I mean, if you make that laptop, they'll make the thing so that it works and then see how much of a fan they got to put in. But they don't have a controller.
Yeah.
They only control the speed of the fan. They're not having a controller that adjust the working of the system based on the temperature.
Yeah, this method
So-
kind of treats dissipation on equal ground as the other mechanics.
Right.
It's built into the system. So for economic system, this could also be interesting because we would have a forward factor, a discount factor built into our mechanics.
Yeah, so you could make the claim that you're, after having put energy back in control, you're also putting energy into control.
Yeah.
And
exactly.
there's no back needed because it never was in there to begin with.
Yeah.
Right? Huh?
Yeah.
So you're doing a little bit more than they are. They got to do without that form of energy.
Yeah.
So they're not using the first law of thermodynamics. They're just looking at the mechanical or the electrical energy,
Yeah.
right? The available energy, not at the
Yeah. Exactly.
Huh?
And because
Anyway.
I can see why that is, because the stored energy that is also oftentimes the Lyapunov function of the system.
Right.
So their thinking was, okay, we can build that into our formulation
Right.
and then we can get away. But that was wrong because you're doing energy-based modeling, energy-based mechanics without accounting for all the energy.
Yeah, so the stored energy, there's also energy stored in that cooling device.
Yeah.
And that they're not taking into
Exactly.
account. So
Yeah.
and then of course you didn't really put energy back in control. You put some energy back in control, but not all of it.
Yeah.
Right? So if I look at the first law of thermo, it says du is dq minus dw, and all you did was that dw term. You put in all the work in there, sure.
Yeah.
Thank you, but you forgot, huh?
Yeah.
You forgot the heat, huh?
Yeah.
So you're still pretty cold.
I have one more question about passive controller. I'm trying to understand because I understand that you don't add energy because then it wouldn't be passive. You can increase the net energy, but if there's always a decrease of 2, and my controller adds one.
Wait, so what controller are you talking about?
Passive controller.
The
So
passively based control.
if I recall correctly, you mentioned that it doesn't work because you cannot add infinite energy.
Yeah.
And because you defined it as a controller that energy is either the same or it decreases, right?
Yeah.
But if it decreases by 2, for example, and I keep adding 1,
Yeah.
it still fits your passive controller definition. And why couldn't that work? Because if I look at the passive controller as a bank or like central bank, and I can keep printing money, there's no limit on how much money I can print. So that would be my infinite incentive I can put in there. But as long as the total energy it's not increasing, I would still be able to use that method. Right?
Yeah. So you kind of answered your own question. If the bank keeps printing money, well, then we will have a massive problem because it will degrade the value of the money. So in practical sense, it wouldn't work. But what if I understand correctly, you're saying, okay, suppose the system is going down by 2, and I inject 1
Yeah.
for the controller. The point is that my system, even at equilibrium point, the point where I'm going to the end point, is dissipating energy. How much is it dissipating? Well, it depends how long you let it go on, but we should be able to keep it there infinitely long.
But like you mentioned, that's an equilibrium point.
Yeah, of the total system, the closed loop system.
But how would that be dissipated? Because that would mean it would lose some energy, so it would not be an equilibrium, right?
Yeah. So that is the problem. So if you take this system, this closed loop system, I can design my spring and my damper in such a way that if I let it go, then the mass will nudge a bit to the right. And when it is at a new equilibrium, there's no energy flow. Whatever. For this system, there will always be a current going through that resistor. There will always, if I am a supplier and I have stored some goods in my inventory, they are going to appreciate. So if I want to increase my inventory, set it to a non-zero point, for example, well, I need to keep supplying an incentive, keep the flow
I
running.
see what you're doing, yeah, because on the left side, you design the system that if you go to the equilibrium point,
Yeah.
nothing's happening, and then the right side, you're always dissipating it.
Exactly, you need to keep dissipating, to hold it at that new equilibrium point.
Okay, well then, remains just to thank you. Well, very nice.